Today, very important lesson for equilibrium is Le Chatelier's principle, and we're going to use this to decide if something happens to an equilibrium that's in, a system that's in equilibrium, how does it get affected by that change? So, definition, external stress, what kind of stresses are we going to be talking about? Changes in concentration, if it's a gas, changes in pressure or volume, and then most of these things, if the delta H is known, then we can also talk about in terms of temperature. Okay, and so that'll be an external stress, and if it's applied to the system at equilibrium, the system will have to readjust itself to get back to a new equilibrium. If we are wanting to show this mathematically, we're going to use this using our reaction quotient, Q. And we're going to compare it with a K if a K is known. But if the K isn't known, we can still compare Q and K by just saying that Q will be going increasing or Q will be decreasing. And that will help us decide, is the reaction going to shift more from left to right at that point, meaning that if we're looking at an ICE table, we'd have negatives for the reactants and positives for the products. Or we might have the circumstance where the stress to the system is going to create a situation where the products are more likely to go back to the reactant side, and we'd have changes that would reflect that. Okay, so here is a typical kind of question. This one, lots of people do this in the lab in AP chemistry. We do this also in the lab. So we have a compound, not a compound, we have a solution here that is red. Actually, a lot of people define it as blood red. And then it makes a couple components here that, yeah, I called that pale yellow, but you'll almost see this as clear. So if you have something that favors the reactants, you're going to have a test tube that is has a red solution in it. If it favors the products, you're going to have a test tube that has a more or less clear solution in it. And then anywhere in between that kind of gives you an indication about more to the product side, more to the reactant side. So here's some circumstances. So if we add SCN, yeah, we got the sodium in there, but if we add that, that is this material right here. And if we do that, there's going to be more of the products to be able to run into each other, to collide. And if you have more collisions, you have more opportunities for reactions to occur. So this is more likely to shift back to the left-hand side. Don't have a lot of room here, so I'm going to put it right in the middle here. We could also talk in terms of Q. So Q has products up top. So I guess in this case we'd have iron plus 3 and SCN minus. And on the bottom we'd have this blood red material. And if you would have increased the SCN minus, the Q would end up being a bigger number. And what does that mean? If the Q starts to become bigger than the K, or even, I guess, increase from its previous point, that means shifting to the left. If the Q is getting smaller, something would happen where that would occur, then the reaction is going to shift that way, K being bigger compared to the Q than what was previously known. Okay, so we'll practice that a little bit more for sure. Let's take a look at iron nitrate. Iron nitrate is going to give us, so kind of let's erase some of these items. The iron nitrate is iron plus 3 ions. if you would add iron plus 3 ions, it's going to have the same result. You're going to have more opportunities for those products to collide and make the reactant. Another circumstance, sodium carbonate. Sodium carbonate, I think I have it written here, would be able to precipitate the iron ions to make iron carbonate. So it's as if you've taken iron ions out of the reaction vessel. So what's going to happen in that case, you're going to have less of these products to be able to collide with each other, and it's going to shift the reaction from left to right. Okay, and because there's a red involved here, we can also have talked not just about shifting left and right, but what we would have been observing in this reaction vessel, this test tube I guess I was mentioning, and I have these in parentheses there. By the way, that's not the only things you could do, but those are 3 circumstances that I kind of thought about. Here is the same idea, but graphically. So we have our 2 reactants going to 2 products, and it's a dynamic equilibrium situation there. And it's at this point in that dynamic equilibrium until you do something, until you put a stress on it. And it looks like the stress is going to be that we added some B. So if you add B, by the way, Q is, these are often concentrations, but I guess these could have been partial pressures. No, not in this one. This says concentration, so let's keep these concentration. So if we add more B, that's the bottom of this fraction, it's going to end up making Q become a smaller number. And the K is not changing, but the Q is changing in relationship to the K. And if that occurs where Q becomes smaller and smaller, then it's going to shift the reaction. And let's talk about this shifting of the reaction graphically before we talk about it in terms of this Q, I guess. So if you add more B, it's going to shift the reaction that way, and you're going to have to lose reactants and gain products. Did we lose reactants? Yep, reactants went down. Again, products went up. And then, of course, at some point, you're going to reach that new, it's hard to tell exactly where that's going to be in time on the x-axis, but you're going to go fully horizontal, and then you've reached a new dynamic equilibrium situation. And at that point, this could be continuous. You could have another change. Let's this time take B out. So if we take some B out, then you're going to have that situation occur. So you would have to make more B, you'd have to make more A, you'd have to use up your products. And I don't have enough room to continue that on until it would reach equilibrium, and then you could do something else again. So these aren't static, they're definitely dynamic, and you could continue to do this over a period of time. What else could we do? So if, again, I mentioned if you have something that has gases in it, then all the gas law ideas can come into play here, like just adding more chemical, more partial pressure. You could change the volume, but then there's things that you could do that won't have any effect. If you added inert gas, nowhere in the equilibrium expression or in the reaction quotient expression is there any place for an inert gas. So you're not going to have that affect anything. Catalysts would just get you to equilibrium faster, but once you've reached equilibrium, it's not going to have any effect. And then this one's interesting here, P4. P4 is a solid. If you remember from heterogeneous equilibrium expressions, that those solids have no effect also because they're not in the equilibrium expression. So it has to be there, but it doesn't matter how much. As long as there's some P4 solid in this vessel, then the reaction will continue in that dynamic equilibrium. Okay. Okay, so let's see what would happen here. Predict the direction of the net reaction. Okay, and again, we could always talk in terms of Q, and Q is all those products, and then on the bottom is all the reactants. And I didn't want to put brackets or partial pressures because it's going to change depending on what the question is. But and yes, the coefficients become raised to the powers of also. So let's see, increase in the pressure. Well, that would increase the O2, but it would also increase the SO2. Well, do they increase each by the same amount? No, it's a 3 to 2. So a lot of people can actually just go like 3G, not grams, but 3 gases. If you don't like that, 3 gases going to 2 gases. So you're having more effect on the reactant side. There's the reactants. So that's going to make the Q go down over a period of time. So the Q versus K, if the Q gets smaller over a period of time, it shifts it to the product side. If you were trying to use, trying to explain this on a free response question, you would want to add those items. So the Q idea, I know we don't have any numbers to put in there, but we have a theoretical, you can use those up arrows and down arrows. That's kind of universal, and everyone knows what you're talking about if you do that. The next one, if you increase the pressure, it's like as if you increased H2, but you've also increased CO2. You've also increased H2O gas and carbon monoxide gas. So it looks like 2 gases and 2 gases are affected. Well, with the information provided, it would be impossible to see if there's going to be any net change here, direction change. So I think we'd be better off at this point saying no change, and that would be acceptable on a test. Now, if there was more information provided, we could go with that, but with what information is provided right there, I think we're going to have to say no change. And then the last one here is CO2 is our only gas, and that's a product. So let's go back to our Q up here. So we've increased the product, which means we would have increased the Q. If the Q gets bigger in relationship to the K, it shifts it that way. Okay, I guess you could also talk in terms of collisions, and because you've added more CO2, more collisions, and I think we could have used that idea with this first one here also. Okay, so temperature can also have an effect. So how does temperature have effect? Well, the delta H for this reaction is given. What does that really mean? That means that 92 kilojoules of energy can be written as a product, and that means you're losing 92 kilojoules of energy for every mole of reaction. So it's as if we have another product. At times, if it's an endothermic reaction, we have another reactant, and we can think in that terms. So if you would add heat, it would be like as if you're adding a product in this case, and it would shift it that way. We can't really do the Q versus K in this idea because energy is not in that reaction quotient. So we're going to have to leave that out for this example. But if you would chill this reaction, you would be taking energy away, and it would shift it to the right. And people do use those methods to manipulate these reactions to either try to produce more product or make the reaction go slower. In this case, this is ammonia ammonia is a nice building block for fertilizers and explosives, and a lot of people manipulate this reaction, and they can do it a number of ways, including with the temperature. Volume is doubled. So it doesn't specifically ask us any numerical value, so we're just going to say volume goes up. If the volume goes up, any gases in there, their partial pressures are going to go down. So down, down, down. We have 2 gases going to 3 gases. So it's as if it affects the products more. So you're going to have less collisions on the product side, and it's going to shift to the right. We'll talk in terms of O2 in a second here, but you can also talk in terms of Q. Remember this, these are products up here, and these are reactants down here. So if the products go down, Q goes down, and that's going to shift it to the right, just like we mentioned before with collisions. And O2 is to the right, it's a product, so the concentration of O2 has to go up. Okay, we have a decomposition reaction here. You add calcium carbonate. Unfortunately, calcium carbonate is a solid, not unfortunately, but it's a solid, and solids aren't in the equilibrium expression or in the reaction quotient expression. They have no effect on this reaction, they just have to be there. So no change. Catalyst, it just gets you to equilibrium faster, so it would have no change at the new equilibrium for any item in this reaction. Inert gases, same thing. They will have no effect. Okay. By the way, this reaction, now, it's just a chemical reaction, but an individual named Fritz Haber, H-A-B-E-R, or Haber, he was able to figure out how to manipulate this Le Chatelier's principle in a way that no one else was able to do before, and optimize this reaction to make a lot of ammonia. It's actually difficult to make this occur because you have to break that into the bond between the 2 nitrogens. That's a triple bond, and it's a very stable bond. It's very strong, so it takes a lot of energy to do that. So what could we do to make more ammonia? Well, a whole bunch of things. You could take N2 out. No. That would not work. Sorry. If you add N2, reaction shifts to the right. If you add hydrogen gas, shifts to the right. If you take some of your ammonia out, maybe put it into a its own container and ship it wherever you want to sell it, that would be able to shift it to the right. What do we got here? We got 4 gases going down to 2 gases. So if you took the volume of the container and made it smaller, the partial pressures of everything would go up, which would be as if you added reactant, and it would shift it to the right. Those would all work. And you could talk about collisions with all those that I just mentioned. And you can also talk in terms of Q, products, and reactants down here. And you can talk in terms of that. So if someone says validate your answer, collisions or that Q versus K idea is where we'd want to go with that. There's also a delta H given, meaning that this is exothermic, and you could also manipulate the temperature. So if you wanted to make more ammonia, if you would chill this reaction, you would actually shift it from left to right also. Here are a couple equilibrium reactions that I think are kind of important. Hemoglobin. Hemoglobin is not a equilibrium by itself, but you might be able to notice this. I've never climbed Mount Everest. I don't plan on doing that, but you have to acclimate yourself over a period of time, and this to kind of manipulate this equilibrium here. So if you go to climb Mount Everest or any other high mountain that's high altitudes, and at high altitudes there's less O2. So if there's less O2, there's less O2, and that means you're going to shift the reaction that way. You need this in your bloodstream. The hemoglobin with the oxygen is then going to go, the red blood cells are going to move, your circulatory system is going to move that to all the cells in your body, and if you don't have that, then your cells in your body they're not getting the oxygen that they need. So what could you do? So your body would manipulate itself and produce more hemoglobin to offset the less oxygen in the atmosphere. And if your body makes more hemoglobin, now it shifts it that way. So that's what I mentioned here. And I already mentioned the Haber process. And there are some other equilibriums in your body. I have one down at the bottom here. Carbonic acid plus water makes bicarbonate and hydronium. And certainly that's not the only way that your body maintains homeostasis as far as pH, but very important equilibrium process there.